So, right here. So this is basically 120 degrees different from each other at different timing and different voltages. That's what three phases is, right? That's where we stopped. So we know V equals IR, W equals VA. Those are the basics. DC is just one way flowing, so positive to negative, and then alternating, which is double way flowing, and RMS, which is root mean square. And yeah, I need to double check on this. So let's say like RMS question mark. So let's make a few like that. Three phase, we know what this is. And then motors, we have star and delta. So star is basically, yeah, I need to double check on that as well. And then we'll do, okay, so this conductor, we know it's copper and aluminum for lighter and cheaper it works. And then more current, if the thicker the cable, the more current that can flow. The voltage drop limit is less than 3%, which is what we have over here. Miniature circuit breaker, this is what we have. So I have, so we have the, what's it called? Bulbers, no, breakers. Bulbers, was it? Bulbers. Breakers, isolators. So we have isolators. So yeah, busbars, my bad. So busbars. And then we have breakers, which is MCB, and we have isolators, and then we have load balancers. So this is basically after the supply. So from this could be the what do you call that? The transformer, or the yeah, so the transformer basically. And then busbars to the breakers. So the busbars are the little things that basically connect to the breakers, and then the isolators are the ones that basically allow you to manually disconnect the circuit for maintenance. And then load balancer balances out the load evenly across phases, as you can see. So balances load evenly across phases. Right. So boom, just like that, we have a single line diagram for this. So the next one is basically, so miniature circuit. So RCD and LCB is for human protection, for leakage detection and stuff like that. So let me just double check on this. So as you can see, we have one second. All right, right here, let's say, my bad. So RCD is basically to prevent the so live and neutral flow, RCD motor, exactly. So RCD is basically detects imbalances and current leakage to earth/person, and RCD trips power disconnect. So in case there is an imbalance in the current that flows, the RCD disconnects. So let's double check on that. Does RCD disconnect when there's an imbalance in power flow? Yeah, okay. So RCD disconnects when it detects some imbalance in power flow, right? Basically it trips a switch, and it disconnects by tripping a switch, question mark? Yeah, okay, so the RCD disconnects a circuit by tripping a switch when it detects an imbalance in power flow. So let's see if this is the same concept for ELCB. Yeah, okay, so earth leakage circuit breaker. So this is the ELCD and the RCD residual current detection, the same. Okay, so well, both the RCD is modern. Okay, so the RCD is modern, and the other one is basically old. So let's say RCD modern, and ELCB is old. So RCD is both. One second. So both protect against electric shock. The RCD is modern, current operated device. And the term ELCB refers to an older voltage operating device. RCDs are more sensitive, don't require a separate earth connection to operate, and can detect a wider range of faults, fault currents than the older ELCB. Don't require a separate okay. So let's have another point here. RCD is more sensitive, so let's say more sensitive, don't require a separate earth connection to operate, and then we can detect a wider range of fault currents than ELCB. I will say older, both And the term ELCB now refers to an older voltage operating device. Exactly. So electricity load current balancing. What was it called? Earth leakage circuit breaker. My bad. So earth leakage circuit breaker. So let's say, for example, earth leakage circuit breaker equals earth leakage circuit breaker, which is older. Okay. And yeah, so that's that. That's that MCB. So this is the MCB curves. So it's basically the kind of power voltage, I believe. Sensitive, exactly. So sensitive trips really quickly. That's for home use. A moderate. So C is moderate for general circuits, and D is for high inrush current equipment. So that's, I believe. Okay, so BCD, right? Okay. So we have transformers, welders, which is for D. Motors and fans for C, and then lights and heaters for B, which is so the MCB curve. So indicate the amount of overcurrent a breaker will tolerate before it trips, which is crucial for matching the breaker to the electrical load. Right. So let me see. MCB curves. The amount of overcurrent a breaker will tolerate before it trips. Right, which is crucial for matching the breaker to the electrical load. So let's simplify this. Let's say indicates amount of overcurrent, right? For trips, which is crucial for matching the which is crucial for matching the breaker, the electrical current. Okay, so it's much simpler. So indicates amount of overcurrent the breaker will tolerate, right? And before it trips, right? Matching the breaker to the electrical load. So other than that, so T and S, so TT and TA, so let's say, so O and Earth, supplied Earth, T and CS, which is shared Earth neutral and splits. So let's get a better understanding of this TT systems. So let's understand why earthing is there in the first place, which is L and E, right? So usually it would be like, let's say for example, where is it? So we have L in every pin, we have L, N, and E, which is the top one. So pretty much this is live, neutral, and earth. So let's understand what this is. An electrical grounding system arrangement where the power source is grounded at the supply to the point. Is grounded at the supply point, and the customer's installation is independently grounded with its own earth rod. Right. So customer's installation is independently grounded with its own earth rod. So let's go back to this idea. So it has its own earth rod. So electrical grounding system arrangement where the power source is grounded at the supply point. L and E, okay, no, supply point. And the customer's installation is independently grounded with its own earth rod. Okay. So let's say O has its grounded with its own earth rod. And what is TNS? I believe supply is already there. Keeps the neutral and protective earth conductors separate throughout the entire installation. So keeps neutral and okay, connecting the main earthing terminal to the distributor's supply of separate conductor via the right. Okay, so much. TNS, the protective conductor, good ground conductor, is separated throughout the system, right? So it keeps the neutral and protective earth conductor separate throughout the entire installation. And TNCS, which is combines the neutral and protective earth conductors into a single pin. Protective neutral conductor in the supplies authority cable, which is then separated into distinct neutral and earth conductors within the installation. Interesting. So let's say combines protective earth conductors into a single pin conductor in the supplies authority cable, which is then separated into neutral and earth conductors within the installation. So yeah, that's pretty much it. So we have rings, obviously, for this ring is basically for you know, outlets type of thing, and then we have the like the radial, which is basically for line, like inline socket, like lights and stuff, like, you know, you get what I mean, like lights which appear one by one. 10 minutes so far, that's good. Okay, so ring versus radial, exactly. Breaker, wire size must match, exactly. So let's say breaker, wire sizing is important. W equals 3A, yeah. DOL, which is direct on-line diagram. Variable frequency detection, transformers, step up down. So step up down is basically for transformers which have to distribute the current up and down depending on it, and sometimes there's losses measured in copper and iron. And let me just double check on that. A transformer, when transformers step up and down, the loss is measured with copper and iron, question mark? Okay. So transformer losses are measured in both copper and iron losses, regardless of whether the transformer is stepping up or down in the voltage. Copper loss or winding loss is due to the resistance of the wires, while iron loss or core loss is caused by the alternating magnetic field in the core. Right. So basically, right. So regardless, transformers, copper loss or winding loss is due to, so let's say, copper loss, resistance of the wires, and then iron loss is caused by alternating magnetic field in the core, right? Alright, let's get a picture of this real quick. So I'm just gonna grab this real quick. So this is a step down transformer. So let's see where the iron and core loss. See where the iron and so as you can see, this was the step up and down transformers. So where let's see the iron transformer, iron and copper loss. So we have where is it? So this is iron loss. This is copper loss, is it? This is not simple as like left and right? Iron losses on the left and copper losses on the right. Exactly. That's also, that was such a dumb question. Just want to make sure. Iron losses occur in the transformer's core, copper losses occur in the windings, exactly, okay. So, where is it? Can't type for shit. Where is it? Okay, well. So this is the iron loss, and this is the copper loss, okay. Edgy current loss. What the hell is that? Hysteresis loss? What the hell is that? Okay. Copper loss. Okay, well. Let me get a better picture. This will do the job. Panels, main bus bars. So it's basically from the main supply, you get the bus bars to the, so the bus bars are the ones that take you to the breakers, and the breakers are the ones that put to isolators, load balance, single line diagram. So bus bars, breakers, isolators, load balancers. So bus bars, so supply, it's like current supply, so it could be a transformer. So a bus, then to the bus bars, and then to the breakers, and then to the isolators, and then to the load balancers. And that you can represent it with a SLD, which is a single line diagram, which is what we have over here, right? And industrial control, so we have contactors, relays. So contactors are basically, I have another thing about this. So control logic, so programmable logic control, right? So we have relays and then contactors to motors, right? So pretty much contactors, relays, overloads. So contactors power switching, relays control signal, and then overloads motor protection, exactly. A PLC, so overload protection comes here, and then motor protection, PLC, automation, and logic brain, exactly. So contactors, relays. So we'll keep these things simple for now. PLC, contactors, relays. So relays, contactors. Okay, so relays first. So let me just get this in order, so it's easier. So relays control signal. Contactors are pretty much power switching, and then motor, which is motor protection that happens with overloads, I guess. Takes more, yeah. So overloads or OLR, which is motor protection from excessive current, and PLC, which is a programmable logic controller. So that I assume is the last one. So basically, relays, overloads. Wait, why is this two different ones? Okay, contactors first, and then relays, and then overloads, and then PLC. Why is this like this then? So let's be to ChatGPT, and let's say correct this. All right, there we go. So, okay. Rewrite what I gave, what format, so I can copy. Yeah, so, yeah, that's pretty much that part. So let's move on. So this is for testing and stuff. So measure continuity, loop impedance, and multimeter. So multimeter and clamp. Clamp is the one with the crab claws. Multimeter is the other one with the two forks. Load calculation, diversity, cable chart, short circuit calculation. Yeah. So this is LNE, live, neutral, and earth. We know how it goes as well. I just wanna. So this is a L, N, and E. Boom, like that. So this is live, neutral, earth sockets. Ohm's law, yeah. Ohm's law is W equals V, is it? No, V equals IR is Ohm's law. Okay, yeah. So Ohm's law is V equals IR. So let's copy this real quick and let's paste that here. So logic control, relay, contactor, right? And then motor, overhead, overload, motor protection for excessive current, and PLC, automation, and logic brain. So once that is done, so domestic wiring, device sizing, motor starters, single line diagram, fault tests, instruments, panels, PLC, solar, backup systems, exactly. And as you can see, we have this right here. So once again, local demand, insulation. So this is a insulation resistance test, right? So it's a mega insulation resistance test. So that's what is IR? No. So V equals IR, right? So I is the current flow, and then R is basically the resistance against it. So it's basically what makes a voltage. So what is I in V equals IR? I think it's the current flow, the part, the pressure of the current. Yeah, current. So V equals IR, so represents exactly. So that's what makes a voltage. So I V equals IR. I is intensity, pressure of current, and then R is basically resistance, pulsing, and insulation resistance. So what is insulation? What is insulation resistance? The measure of a material's ability to prevent the flow of electrical current. Measure of, right, so let's say, and ability, material's ability to prevent the flow of electrical current. Let's put that here. Resistance test, and that's pretty much it. So V equals IR. There we go. Okay. Cool. Nice, nice. Alright, that's pretty much it for now. So Mango continuity. Continuity is like basically the thing that makes sure the whole loop is pretty much working, I guess. So continuity is what is basically... One second. I think I clicked the... My bad. What is continuity in electrical? Presence of the complete unbroken path, exactly. That's what I'm saying. Multimeter clamp. What is impedance? The total opposition to current flow in the path of a fault, exactly. So loop impedance forcing. I probably already have it actually. Fault current check, right? Measures the total resistance of a current circuit loop, exactly. Total resistance, make sure there's no breaks. This is measures the insulation resistance of cables and equipment. And finally, we have the one that measures voltage, current, resistance, and continuity. So I'll grab this again. And let's say... Done. Alright. So this is just a touch up on the very surface level of stuff. Industrial control, contactors, relays, overloads, yeah. The load calculation, diversity cable chart, that's all this is good. So single, okay. Let me just double check, because IR. Yeah, so MCB, RCB curves, exactly. Vital for safety. Yeah, so you need this low resistance pad to ground, right? TNC, again, we know what this is. Ring versus radial, socket wiring, so we need for ring for sockets and radial for circuits, like lighting circuits. Breaker and wire selection, exactly. So star and delta, so that's basically, I need to double check on this. Star, delta, star, delta, where is it? Starter, so variable frequency drive, or detection, variable frequency detection. Step up and down, primary, secondary windings, right? Okay, so primary, secondary windings, main switch bus perspective, yeah. Single line diagrams, like load bands across phases, contactors, relays, overload protection, PLC basics. And insulation tester, exactly, design and load demand calculation, I see, and okay, so what we need mainly right now is star delta starter, motor, star delta starter, and star delta starter. Let's see what the difference here is. Method for starting three-phase AC motors by initially connecting the windings in star configuration. AC motors by initially... Okay. So let's say I'm too lazy to read this, so I'll say give this in format. Star connection reduces starting current to 1/3 of normal running current. Delta connection provides a full normal operator. Give it in. Okay, so reduced, okay. So let's say star. There we go, we have a picture. Star, delta, and this is the main. So star reduces starting current, motor accelerates to less than 80% speed. This is less than, right? Okay, that's done. So let's say so less than. So let's have a less than like this. 2% speed. So yeah, that's pretty much it. Variable frequency drive, buspers to the breakers to the isolators to the load balancers to the single line diagrams to contactors, relay to overload protection. I will double check on that part, and once we're done with that, we should be good to go. Universal power supply systems. Okay. Socket wiring, lighting circuits. Alright. Yep, there we go. Alright guys, I think I'm gonna take a little bit of a break. It's been 27 minutes. Thank you guys so much for watching. Let's do this again tomorrow. Bye bye.